Hey guys, my name is Adrienne and welcome to Organic Chemistry 2, Part 8 of these recorded sessions. So today, for most of y'all, we'll be going over Chapter 20 and in general, carbonyl chemistry, organometallic reagents, and redox reactions. So, as always, we'll have review first, review questions, 20 review questions, over the chapter, over the material, and then later we'll have the summary. So compare notes, you know, highlight the big topics, highlight the good stuff, right? And as always, whatever works for you, screenshot, taking notes, going along with the video, answering the questions as we go, things like that. Whatever works for you, do what you want. But again, if you're not, if you're just getting the questions and then afterwards you have a question on what's the right answer, or why did I get this answer, just come back, to the video and see what we talked about. And as always, some of these kind of connect. So you might have to go through a couple questions similar to it, things like that. So, but I'll be talking about it as we go. So there shouldn't be any like confusion or too much confusion, I hope. So, yeah, with that being said, let's get started. So, again, you know, pause the video, do what you want, screenshot, make notes, do whatever, but, answer and let's assess. So, for one, I got B. And of course, this is one of those questions that's like, you either know it or you don't. But at the same time, general reactions of aldehydes and ketones, this is carbonyls, right? So what happens we talk about other carbonyls? So for aldehydes and ketones, they undergo, like we said here, nucleophilic addition, right? But carbonyls with leaving groups do something different, right? So carbonyls with leaving, I keep writing the G first, but leaving groups undergo what? Nucleophilic substitution, right? And that's important because, again, with addition, you have the attack and the protonation, right? And then carbonyls with leaving groups, you have the attack and the loss of the leaving group. So that's the only thing different about that. But again, this is another, one of those questions that you can manipulate, you can turn around, you can ask something completely different, and still have that, be able to answer the different answer choices, if that makes sense, right? So good. Two, you guys should have gotten D, right? So why are ketones less reactive than aldehydes? And when it comes down to it, ketones, right, are more hindered than aldehydes, right? So, and that's what it says here. Both A and B are true. Sterically hindered, ketones are less electron deficient as well, because again, we know these methyl groups are donating groups, right? Donating group, donating group. So again, we're still using those terms from a couple chapters ago. Withdrawing groups, donating groups. By now, you guys should be familiar with them. If not, review them real quick and you'll pick them up pretty fast. So 3, rank following compounds in order of decreasing reactivity and nucleophilic addition reaction, starting with the most reactive. So we just kind of answered that with 2, but this time with actual molecules, right? So for 3, you guys should have gone B. And in general, B, um, aldehydes are going to be the most reactive, right? And and 2 and 4 are both aldehydes. Are aldehydes, while 1 and 3 are ketones, right? Ketones. So obviously, 2 and 4 are going to be the greater, more reactive ones compared to the ketones, right? The 1 and 3. So now, how do we decide, right? Well, we ended up with 2 as the most reactive because 4, again, going back to the donating groups, right? 2 is just a plain old aldehyde, while 4 is kind of like um, a bigger molecule, right? And you see that this is a bigger donating group than this one. So donating group, right? So it's donating more, meaning again, it's less electron deficient, right? Okay, so for now we're getting to the good stuff, the reactions, right? The reactions are always the good stuff because either they're very similar to the ones we've seen before, just sometimes we've even seen them before actually, and then we just keep repeating them, right? Or they're so popular that we just keep seeing them, or the attack is the same, the concept is the same, what have you. So, 4, you guys should have gone something like, let's see, D, right? So what happened in this case is a reduction, and PDC is one of those famous reductioners, right? I don't know if that's a word, but PDC, reduction, reduction. So no surprise there, we've seen PDC a lot. So nothing too crazy. So let's go to 5. Which reagent can be used to reduce carbonyl in methyl vinyl ketone? So again, another way of asking a question, right? So we know number 4 is the type of questions we usually get, but you can also get something like 5 or like even 6, right? Kind of like a different way of asking it, but it's still the same question, it's still the same reaction type, right? So 5, you guys should have gotten A. And this one is a good question too because we know for sure it's a reduction because it tells us in the question, right? Reduce carbonyl in methyl vinyl ketone. So A and B are both reducers, right? But A reduces carbonyls while B, so B is not the right answer, reduces alkenes, right? So big difference. Um, and vinyl ketones, right? Vinyl ketones have double bonds, but we only want to reduce the carbonyl, right? So that's why we chose A. So that distinction is very important, right? Okay, 6. What reagent can be used to reduce amide to amine? So this is a fun one because amides and amines, you'll see a lot of nitrogens in this chapter actually. So what reagent would be used? 6 would be C. Let's see, C, right? So again, we know lithium aluminum hydride is one of those again reducers that we always see, and this time we're just reducing an amide to an amine, and amides are that carbonyls, right? So nothing too crazy. And again, amide is the one with the carbonyl group, right? While amine, oh, okay, let me just send them to. It's just nothing. There's no carbonyl, right? So it kind of turns like this. Um, yep, nothing too crazy. And again, amine, the N for single bond, right? Single. So, okay, nothing too crazy yet. Just general reactions. Pretty much know your reducers, and we've seen all of these before, right? Okay, so new page, same attack, I guess. Pause the video, do whatever you want, and come back and see what you guys got. Okay, 7, you guys should have gotten what? Why would the alcohol in the following compound need to be protected? So, this one's always a good question in terms of like confusing students. But as long as we know what protection means. Like, why do things need to be protected, right? It should be um, it should be conceptual. I should say it's not very specific. It's just conceptual. So in this one, you should have gone B, right? Because again, without the protecting group, um, that means that OH in the reactant is very vulnerable, right? So if it's vulnerable, then that means we need to protect it, and that means if it's not protected, it could have been reacted with, or it could have been messed with, right? So when we protect a group, we want it safe, we want to keep it still, right? We want it to be the same. So A, if it isn't protected, the product will be a carboxylic acid. Not really, because Grignard reagents don't do that, right? They just add on the methyl group. Um, C, magnesium is Lewis acid and will coordinate with the alcohol. Magnesium is not a Lewis acid by itself, right? There's no need to protect the alcohol. There is, because if it wasn't protected, the Grignard reagent would have attached to that where that OH was, right? So things like that. 8, what reagent can be used to cleave silyl ether? So this one is also a good one, right? Protecting groups. We're talking about protecting groups in these two questions. So 8, you guys should have gotten C, because pretty much all you need to know for um, cleaving protecting groups is that you need fluorine, pretty much. Groups need lots of fluorine. Fluorine. So out of all those, it's just C, right? And actually, that C is actually one of the most common ones that will cleave those protecting groups. So because we don't want to keep protecting the group, right? We want to keep it there and then take it out because we want the original, right? So that's one of the common ones. So 9, let's see. What is the major organic product of the following reaction? So SCBS is going to turn into R, right? So 9, you guys should have gotten B. And this is, again, hopefully you guys remember your R and S configurations, things like that. Um, because again, SCBS turns to R product and then vice versa, right? So review for the RNS. We know fourth group in the back, right? If anything, if you can summarize it in in the shortest possible term, that's it, right? Okay. 10, you guys should have gone, what is the major product of the following reactions? Vibal H. So this one's also a good one. You guys should have gone D, right? And what does Vibal H do? It just cleaves, right? So it just pretty much cleaves the ester. And we know this is an ester, right? So the starting product is basically this. And sometimes it's hard to know it's an ester because when they do OCH3, that type of thing. But this is an ester, right? And Debal age cleaves esters. So it pretty much just cleaved it right here, right? To make that fourth. So it cleaved it right here. And this is answer choice D, right? And then this other half would end up like this, right? This would be the other product, I guess, right? So basically, Duval H cleaves esters to form um, a regular carbonyl, and then the other half of the ester group, right? So that's it. Oh, okay. So again, new page, same procedure. pause, stop, get your notes out, answer, things like that. Okay, you're back. 11, you guys should have gone A. So this one's what? Rank the carbon metal bond in the following organometallic reagents, decreasing polarity with the most polar. So as always, 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 it's always gonna be this. This is gonna be the what's it called? The order. Lithium is the most reactive, most everything, pretty much strongest, whatever. And then one second, cuprates, their copper lithiums are always going to be the dead last, the weakest, things like that. And keep that in mind when, and I guess I'll put always, always. Keep in mind when you're using these reactions because weak um, organometallic reagents can't always, go all the way through the reaction, but stronger ones can keep reacting, right, forever, or not forever, but like multiple times, right? Okay. 12. What is the product of the following reaction? Li, lithium, H2O. So this one's a good question, actually. So you guys should have gone what? Right. So if you guys got B, tell me why. So we have this. This is what we're given. So keep telling me why, I can hear you. So what is happening in this reaction, right? So we can even take it further and pretend that this is um we can go further back here. I mean, this is starting from the very, very beginning. So we can make up a thing, and we know, let's see, like a leaving group, right? So this is pretty much organometal reaction, right? So this is pretty much what's happening, right? So we have our um, alkyl halide. We substitute it with the metal, right? So hence the Li. And then pretty much we reduce it with water. And that's why we end up with an alkane. So the name of this reaction is actually RX2 alkane. So, and this is the step you take. You just put any metal in there and then reduce it and get an alkane, right? So nothing too crazy. Okay, 13, right? So 13, what is the range of product of the following reaction? So what kind of organometal is this? Grignard, right? Grignard is one of those things that you'll spot from a mile away. MGBR, MG, well, it's pretty much MGBR always. Um, so it shouldn't surprise you, and we know it just attaches to where the carbonyl carbon is and adds that methyl group, right? So in this one, you guys should have gone what? D, right? And we're not too worried about the S or R configuration because we're just attaching that methyl group and it's going to make a racemic product, right? So let me MGBR, right? It's going to go right there. And that's it. And you end up with 1 and 2. So HO, there, right? So nothing too crazy. We just attach that CH3 group, right? Cool. So now 14 is kind of the same, but actually let me try adding 14 here so you kind of see the visual, the difference in the thing. So 14 is what kind of organic metal? The cuprate, right? Organocuprate. So this time, what should be your product? So this time, we're still also adding the alkyl group, right? But this organocuprate has two, CH3, 2. So do we add both of them, which is what um, choice 1 is saying, or do we add one of them, or do we just cleave the Cl? So this one is also B, because organocuprates, again, they're weak, right? So let me draw this one, CH3, 2, Cu. Right. So it still attacks this one, right? And then this leaving group leaves, we attach the alkyl group. But since it's weak, we just attach one of those alkyl groups, right? So CuLi looks something like this. I'm going to draw it over here. Um, so like that, right? But we just attach one of those R groups. So nothing too crazy. Don't think that you attach both of them, because that's what a lot of people, well, a lot of students think, and they end up choosing one, right? So don't think that. Again, think about the weak, strong um, rankings, right? Okay, so we're going fast, right? So again, pause and take your time, right? Okay, so 15, and just to mention, like, you see how we're going fast? Because you're we're getting more comfortable, right? And honestly, organometals are one of those things that are pretty super recognizable that you don't really. It's not, I guess, as complicated as past, right? And also we're more experienced, so like we should be getting better at this, right? So hopefully, okay. 15, you guys should have gotten A. And again, another type of question um, version, right? We've been talking about a lot of reactions, but this time it's kind of like a little bit different, because this time they're showing it as 3 different steps, right? But we know it's pretty much exactly the same thing. You're gonna have, first you're gonna make your Grignard reagent, right? CO2 acidic workup. This is actually, yeah, different version. But the thing to notice about this is, where's that? You guys might be asking, what's that acidic workup type thing, right? So we know normal Grignard reagent, right? Normal Grignard reagent is just Mg, Br, and then an R group, and we just attach that. But in this case, with CO2 and acid, it makes a carboxylic acid, right? Which shouldn't be surprised, because um, it's pretty much just getting oxidized from that CO2, right? So that's pretty much it, and it just got oxidized. So nothing too crazy. And if you think about it, it's this question you should be looking at is as MgBr and how many carbons? That, and then plus CO2 acid, right? And then you get the product of whatever, right? So that's what you should be thinking when you see this problem, right? We just have a Grignard reagent with whatever and makes carboxylic acid. So, so this is the takeaway from that. So Grignard reagent has 2 functions, I guess, is where I'm trying to get at. Just regular MgBr, whatever, and then adding CO2 and acid to it makes a carboxylic acid. So don't forget that. 16, what is the major organic products? Again, organic cuprate. So this one's an interesting one, because for 16 you guys should have gone A, because why? So organocuprate are weak, right? Are weak. Cannot reduce CO, carbonyl. So, and that's why we chose A, because the only thing that got reduced is that alkene inside the cyclic, right? And the carbonyl stayed the same, so only this part, right? So that's fine. And 3 and 4, well, actually, 3 underwent 2 reductions, right? Which is not right because we know organic cuprates only add one of their alkyl groups, but 3 would have been 2 alkyl groups, right? One in the double bond and one the carbonyl. Um, 2 is completely wrong, right? Because even though it is actually a substitution reaction instead of addition, because that double bond didn't leave. And then 4 is where the carbonyl would have been, right? So, yeah. Okay, so let's go to 17. 17, what is the missing reagent in the reaction below? So, this one, what do you guys get? Again, you guys should have got A. And why A? Because A, because this double bond or this carbonyl stayed, right? So that means we needed something weak to reduce it, which is, again, organic cuprate is the weak one. If we use MGBR, that would have gotten reduced. The carbonyl would have got reduced, right? H2PDC is just a reducer. It wouldn't have done anything. It actually wouldn't even make this product. NABH4, again, wouldn't be able to do this, right? So C and D only work with regular double bonds like carbonyls, right? So things like that. And I know you guys a lot as an SI. I know you guys like of course your tests are not chapter by chapter, right? So sometimes it's hard when they're all mixed together, like chapter 19, 20, 21, when they're all mixed together, it's kind of like hard to pinpoint exactly what you're talking about or what you're looking for because you don't have that chapter title up top, right? Here we know we're talking about carbonyl chemistry, organometallic, and oxidation reduction. So that's what we're focused on. But you know, that's why you need to practice and you need to like see these, and that's why these videos are great because you have 20 questions per chapter, and you guys pretty much know exactly what to look forward to, um, because these will be asked different ways, things like that, right? Each chapter, each topic type thing. So hopefully you guys are thinking about that and not just like memorizing these because that will be bad. That will be really bad. Okay, what is the missing reagent in the reaction below? This one, this one was like the um couple questions back, right? From an amide to an amine, amine to amine, and what did we use then? We used Li, right? Lithium aluminum hydride. So you guessed it, right? D. And you guys might be wondering again, why not Debal? Well, Debal, we said, um, reduces esters, right? Esters, so that can be it. H2PDC, it's not strong enough for that carbonyl, right? Same with NABH4, right? It's strong, but we would have ended up with like an OH group or something, right? So things like that. And as you progress, or I guess we're already in chapter 20, but some things, some reagents, just kind of like, oh, duh, I know what that is already. So take that to your advantage. PDC we've seen so many times, so by now you guys are probably like, okay, it's never gonna be that because I know what it does, right? So okay, so next page. I think this is the last page as well. Okay, so we've done a lot of um, drawings, done a lot of reactions, so now we're getting into the word questions. So take your time, pause the video, and see what you guys got. Okay, 19, a carbonyl carbon and alkene are both sp2. However, the chemistry of these two functional groups are very different, which is super true. This can be explained by which of the following statements. The bond angle, the electronegativity, the bond is longer, there's more steric crowding. 19, you guys should have gotten B. And why is that? Electronegative, definitely. A and C are not quite right because CC bond and CO bonds pretty much have the same length, right? Because they're just double bonds, right? And then A, they're both sp2, so why would they have different bond angles, right? And D, again, steric crowding, they're both sp2, so they have the same angles again, right? So it doesn't make sense. So out of all that, you should have at least gotten B. 20, if the starting material has no stereogenic centers, when carbonyl compounds are reduced with reagents such as lithium or sodium, and a new stereogenic center is formed, what will be the composition of the product mixture B? So this one, again, no stereogenic center to stereogenic center. So you guys should be thinking, are there any specificity, things like that? Going back to an RNS type thing, right? So this one you guys should have gone A because reducing it, we can either have an R configuration or an S or forward back anti-syn type thing. So it's racemic, right? 50-50, we don't get a choice. There's no stereo-specific reactions reducers, right? Again, with lithium and sodium, they told us. So those reagents aren't stereo-specific. So that's it. Nothing too crazy. It was pretty fast, actually. But now we're gonna get into, as always, our little summary, right? So let me close this down. Okay, and let's get started. And obviously, we're gonna be starting with what? Carbonyl groups. And this one's gonna be a short one because we know what carbonyl groups are, right? So carbonyl, we know it's sp2, electrophilic, right? Electro, or I guess philic, right? Electrophilic. Um, that's it. So, as I said, aldehydes and ketones undergo nucleophilic addition, while with leaving groups, nucleophilic substitution, right? And again, this is the process: attack, and then protonate, and then this one, attack, to, and then substitution, right? Loss of leaving group, Ooh, okay, loss of leaving group. Nothing too crazy. And how do we get carbonyls? Or I guess double bonds, how to reduce them. So just real quick, and I don't think this is, yeah, well, I'm doing it over here. So let's say we start with an alcohol group, right? So there's some ways. Okay, hopefully this fits. So we can either H2SO4, PCC, HCl, HBr with SOCl2, and PBr2, TSCl, pyridine. So we pretty much just like a review of like a throwback of the past reagents we've seen before, right? So pretty much for this one, reduce it to a double bond. This one, right? Make carbonyl. This one, I don't know why I chose such a long structure, but again, our halogen here, and then this one, right? So this is like a throwback to like the substitution reactions from like OChem1 and stuff. And again, these two over here could undergo substitution by just adding a nucleophile, right? And then 1, 2, 3, 4, 5, 6, and then that nucleophile would just take its place, right? So things like that, synthesis of kind of just I put this with the carbonyl groups because carbonyl groups didn't have a lot to it, so I just added the synthesis, just kind of like a throwback of like a review. So I guess I should kind of like cut it like that, right? Okay, synthesis of random things. So pretty much throwback to H2S, H2SO4, PCC, things like that. So that's it for the throwback. So now let's get to the good stuff. Um, redox reactions. Redox reactions. So first, we have reduction of aldehydes, ketones to alcohol, right? And this is by the use of NABH4 or LiAlH4, right? And there's um there's an exception or kind of like more examples of it, right? So we can also use H2PDC as we've seen before, and I want to make room. Actually, okay, SCBS. Um, we'll make again the R product, right? RCBS, and these all go to OH, so that's why I'm adding these here. So alkene, if you have an aldehyde or ketone, and then you put H2PDC, it goes to OH. If you put SCBS, it goes to an R product with an OH added to it, right? So that's kind of where I'm getting at. So, okay. And again, this is all racemic, right? So let me bubble it in. So racemic, and that's what we talked about with like the last question. Okay, so next we have reduction of carboxylic acid derivatives. So derivatives like acid chloride, things like that. Um, pretty much a carbonyl with whatever Z group, right? Could be halogens, could be esters, right? Things like that. And they just go to either aldehyde or primary alcohol, right? And there's really no visual to that. We know what carboxylic acids look like, right? And also, we don't have room, and I have a third bullet. So, okay, third bullet. Now we get some oxidation of aldehydes to carboxylic acid. So this one, again, we know what oxidation reagents are, right? As long as there's a lot of oxygens in it, except for O3, because O3, the lysis. But here are some examples. CrO3, so throw back to, I think this is OChem1 when we talked about all of this. Well, actually, no, this is not OChem1, it's like the third the part 3, right? Part 3, which is chapter 14, or no, 12, chapter 12. So CrO3 or Na2 Cr2O3 or R2 Cr2O3. So a lot of different combinations, or KMNO4, right? And also another one here is you'll see later, or I guess not, but Toland's reagent as well. Toland's is another one. So oxidation, and also this one reduction, whatever reduces, right? You can use here too the H2PDC, the NaBH4, lithium, things like that over here. So I'm not gonna rewrite them. Yeah, redox reactions, and there's more. So, okay, so there's more, right? Redox reactions. So we have, and this one's gonna have a title of its own because reduction of acid halides and esters. And this one we have to draw because it's kind of like multiple ones. So again, and this kind of tying to the reduction of carboxylic derivatives, but we're adding esters to it. So LiAlH4 D-ball H2O. So this one will make an OH. This one just cleaves the X, right? So this is not an ester, but it just cleaves it off, right? Oh, let me add the H there. Okay, and then this next one, this is the ester, and this is pretty much showing you the different kind of products each derivative would make. So this one, Li, you see how lithium is just OH in general. Um, Again, this one just H, right? Plus the OH, H, O, and the methyl group right there. So yeah, that's it. You can also use for this one you can also use this really long um, reduction reagent. You can use aluminum hydride, um, OC, CH3. Okay, I'm going to continue here. 3, 3. Okay, hopefully that makes sense. And H2O. So lithium aluminum hydride, um, OC, OH, CH3 parentheses 3 parentheses 3. So a lot of methyl groups, a lot of yeah, a lot of alkyl groups, right? So you can use that as well instead of Duval H, but oh, I forgot Duval H. But you know, so now let's go to the last one, and I'm not sure if these reactions, because I know for sure, depending on who your professor is, they might give you the list or not. But I know these weren't in your book, so you kind of have to like search for them, like a little. like do a little bit of digging to kind of like put them in each section type thing. But so this is how I did my notes. This is how I broke it down. How I kind of grouped them together so it's easier for me in general. I like to see everything on one page, so I would just write everything like, oh, these are all the redox reactions, right, in one page, and that's actually what I have. Right, redox reactions in one page, things like that. So do whatever works best for you, but I like grouping them and putting them in one page so I can see. So when I review, I can see everything like, you know, even in my peripheral, right, I can see the next thing. So like kind of I always associate them with each other, so that's make it easier for me. So this one, reductions, is the title. So we have carboxylic acids, and this is what we saw before, right? Actually, this is we know this. We've gone over it like 3 times already, like in the reduction of aldehydes and ketones and the reduction of acetyl halides to primary alcohols. And then this one is a good one, amides to amines. So, and this is just a note for it. NH2 is a bad leaving group, never lost, right? So if you see a product, an answer choice without NH2, that's wrong because it's never lost. It's just it's always there. Yeah, so NH2 is always there, and it's not gonna get reduced, right? Okay, so that's that with the redox reactions, and now we're going to organometallic reagents. Reagent. So we have this. This is kind of like that one question with the polarity and stuff. This is kind of what the dipole should look like, right? It's going to the R group because obviously metals are not electronegative, carbons are more electronegative, right? So more polar, more reactive, and that's why or that's more reaction, more reactive, same thing. So that's why lithium is always in the group, is all the way over in the group row 1, right? That's why that's the strongest. And then magnesium in row 2, and then copper is like row, like super close, right? So there's not that dipole difference. So we have our organo lithium, so RLI, right? And to make it, you need an RX plus 2 lithium, right? That's how you make it. Organo magnesium RMGX, and to make it, you need an alkyl halide plus magnesium. And again, right, if we add CO2 and water or acid, right, we get carboxylic acid. 3 organo copper or cuprate, right? R2, it's always going to be R2, but we only use R. We only use one R when we're attaching it, right? And you make it 2R Li plus Cu(I), right? So synthesis here. So if you see Rx plus Mg, that's automatically gonna make Grignard reagent, right? Um, and actually, so this is the Grignard. This is, I put organic cuprate already, but then you put organocopper for consistency's sake, right? And then we have two like minor ones. We have acetylide ion, which is organosodium, sodium, and this is what it looks like, or this is how it's made. And this is actually from a couple chapters back when when we were talking about triple bonds, or maybe it was in OChem one, acetylide ions, and pretty much you attach the R group, right? So this R group gets attached, but this is how you make it, right? And then another one we have here is lithium acetylide. So it's pretty much the same thing, actually. Lithium, but the R group is the one you attached, right? So pretty much the same organometal, right? They attach um, R groups. So yeah, organometals attach R groups, and that's pretty much what they're used for. So now let's look at the reactions. Organometallic reagents. So uses first. This is we saw this earlier in the question, but this is how you kind of the general reaction, I guess. So we have an Rx because all of them pretty much requires Rx, right? And then you have your metal choice, magnesium, copper, lithium, whatever. And then you make an Rm, and now H2O, and then you're back to basics, right? RH. So now another tidbit is that strong nucleophiles form new bonds, more CC bonds. So this is basically saying that the whole point of organometals is that it makes alkyl groups, right? It makes the chain longer, the carbon backbone longer, right? So it just keeps adding on. So I guess in a real world type scenario, you can just keep adding alkyl groups to the use of organometals, right? So that's always good. Okay, now one reaction with aldehyde ketone. So let's see here. RH. So either aldehyde or ketone, right? And then we have our metal. And we end up with this. So you see all those, the R group right there. And at the same time, it kind of reduced it, right? It kind of reduced that carbonyl. So, and this is just alcohol, right? Reaction with aldehydes and ketones to form alcohol. And this is any kind of alcohol, primary, secondary, tertiary. So maybe I should just put that there. Now we won't have room. Okay, okay, I'll stop with the drawing. So, um, reactions with RCOH derivatives to form ketone or tertiary alcohol, right? And can we, yeah, Can you guys visualize that? So kind of like pretty much carboxylic acid derivatives. So the best one that I always use is the acid chloride because it's instead of the OH, it's kind of just a CO, right? And you make again. Actually, let's just draw it. The third one will be on the next page, but that's fine. I don't think I would have been able to fit the third one. But okay, so D, right, derivative or whatever. Rm H2O O or RR OH, right? So this one is a tertiary alcohol. So this one's a regular one, right? Regular reaction. We just added the R group where the Z was, so like a substitution reaction. But in this case, depending on the strength, right, of the organometal, this means it's strong because this got reduced twice, right? The carbonyl got reduced. So we can even say this is the weak, right? And this is strong here, right? Does that make sense? It's weak because it didn't reduce that carbonyl. It's strong because it did reduce that carbonyl, right? So, okay, organometallic reagents. So third one, reaction with electrophilic functional groups. Functional groups. So this one has a couple. So this one, so CO2 with again acid H3O plus. We will make that carboxylic acid, right? So like what we talked about the Grignard. And then this one is an epoxide, right? And it just opens the epoxide up, right? And turns it into alcohol. So now limitations. So organometals can't always do it all, right? So why not? So one of the limitations that cannot be used with molecules containing both carbonyl and NHOH. So because these undergo acid base reaction, right? They undergo acid base reaction instead because of the NHOH. Because then we said what? That organometals are strong bases, right? So NH and OH, right? And the conjugates will just make it into an acid-base reaction. So that's why you can't do that. And it's all about the conjugates. It's all about doing all of that chemistry stuff, right? So, okay. And then that's the limitation. Now, let's go over protecting groups. Protecting groups. So, protecting groups we will see this time around is going to be our TBDMS. So if you see that, there's something that's being protected, right? So ROH plus TBDMS plus amine or imidazole will lead to protection, right? ROTB BMS, and you're pretty much left with this, right? So long, pretty much this OH or this H group got substituted with this TBDMS, right? Okay, now to cleave that, you need the fluorine, right? And this is a pretty long one, so let me see if this will fit. The protection or cleaving it off, right? You will need something, let's see, four. So I just abbreviated into this. So R group, right? Actually, let's have R4 and F, right? And that fluorine is the key. And then you'll end up with, again, your original. So this is your one, two, three, right? So that's kind of how protecting groups work. And we'll see a lot different protecting groups throughout. I think next chapter we'll see a new one. So keep that in mind. And now, last but not least, depending on again who your professor is, they might not cover this or even kind of I guess surprise you. So let's see. This is going to be a reaction with alpha beta unsaturated carbonyl, right? So what does that mean? So basically, this is conjugation, but with carbonyl groups. So we know what conjugation is. It's pretty much like resonance. We know what resonance is. So this is kind of just like conjugation, but with a carbonyl group. So let's say we have this, and it's unsaturated, right? So that means double bonds everywhere, and it's turning into this, and this is the conjugated resonated form. So and then I'm gonna draw it in a different color actually. So this is where the conjugation is happening. So it's just right. That's the conjugation, and because of that conjugation, this becomes partially negative, right? Very negative over here, and because of that negativity, this is becoming positive, and also this side is positive as well, right? So pretty much where everything is, right? Now, why is this important? Why do we care? Well, remember with conjugation, what did we talk about with conjugation? We talked about 1, 2, and 1 for addition, right? Addition. So now you have to keep in mind conjugation when you're dealing with carbonyls as well. Because 1 to conjugation, 1 to addition will happen to lithium and Grignard. 1,4 will happen to R2C, organocuprate. So keep that in mind. Um, and the process over here is attack, and 2 is the protonation, and this one attack, and then this is where it gets kind of different, is because it makes the enolate, right? The enolate, and we know enolate, the enol ketol, the enol keto tautomerization, right? The enolate, and the enolate is pretty much just this right here. Those partial positives, right? And then we have protonation. It's still, and then it's the enol keto part, right? So enol pretty much just 1,4 addition, enolate turns into enol, right? And then again this. So you may or may not cover it again. So ask your professor, ask your SI. But pretty much conjugation, but with a carbonyl. That's how I think of it. So with that being said, that's all I have for you guys. Somewhat, no, not too crazy. Next chapter will be crazy. So hopefully you guys stick around. If you guys have any questions, feel free to, clarify with your professor, your SI, but try. Hopefully, I don't confuse you too much, or it's not confusing at all. But you have plenty of resources. Use them. Encourage you to use your resources definitely. So do whatever you want with your, strategies. Whatever works for you. Great. And hopefully you guys join me next time. I'll see you guys around.